Limit properties. Our objective is to use properties of limits and an analytical approach to find the limit of a sum, a difference, a product, a power, a root, a polynomial, a quotient, a composition, an average rate of change, and a difference quotient. Let the limit as x approaches c of f of x equal L and the limit as x approaches c of g of x equal k. C and b will represent real numbers, and n will represent a positive number. Then it is true that the limit of a constant looks like this. The limit as x approaches c of the constant b equals the constant b. Well, that looks simple, and if we think about it graphically, it really is. Drawing a coordinate plane, I'm going to graph a constant function. Let's think about the function y equals 3. It is a horizontal line. No matter what x is, the y value is always 3. So if we do the limit as x approaches any number we want, we could pick 5, of 3, well, no matter where x is going, the y values will always be 3. So we can say the function is approaching 3 because it is always 3. The limit of 3 is 3, no matter where x is going. That property is used quite a bit. The limit of a constant times a function. The limit as x approaches c of the constant b times the function f of x equals b times the limit of that function. So you can think of that like we're just pulling that constant out and doing the limit of the function first and then multiplying it to that limit afterwards. The limit of a sum and difference is also used quite a bit. The limit as x approaches c of the sum or difference of two functions, f of x plus g of x, or f of x minus g of x, is equivalent to the limit as x approaches c of one of the functions, f of x, plus or minus the limit as x approaches c of the other function. We can think of it like we're just going to do one limit at a time and then add or subtract depending on what it says. The limit of a product is very similar. The limit of the product of f times g is equal to the product of the limits, the limit of f of x times the limit of g of x. The limit of a power is really just the limit of a product in a simplified version. The limit of f of x to the nth power is the limit to that nth power. Similarly, the limit of a root, the limit of the nth root of f of x is the nth root of the limit. And then there's one that's very commonly used, the limit of a polynomial function. I like to think of this as direct substitution. Direct substitution says the limit as x approaches c of a polynomial p of x equals p of c. So wherever x is approaching, if we can plug that straight into the function and it works, then we have the limit. And it's important to note that we always try direct substitution first. Because if it works, we're done, and we really don't need to spend our time looking for other strategies. The limit of a quotient is similar to the limit of a product, where we can look at each limit one at a time. The limit as x approaches c of f of x divided by g of x equals the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. However, when we are dividing, it is very important that we do not get 0 in the denominator. So this can only be used provided that that denominator is not equal to 0. Often a good strategy is to just do one limit at a time and see that the denominator is not going to equal 0. Finally, we're going to work with the limit of a composition. Remember, a composition of functions is plugging one function into another function. This property says the limit as x approaches c of f of g of x is equal to f of the limit as x approaches c of g of x, given that f is continuous at the limit as x approaches c of g of x. These will make more sense as we practice them. So let's go. Examples. Use the graphs at the right to find each limit. Notice we have two separate graphs here. We have the graph of g and we have the graph of f. Limit as x approaches 2 of 2f of x plus 1 divided by g of x cubed. We've got a lot going on here, so let's just think about our different properties. The first thing we notice is that we have a quotient. So it's best to deal with quotients one part at a time. We'll look at the numerator, the limit as x approaches 2 of 2f of x plus 1. Then we'll look at the denominator, the limit as x approaches 2 of g of x cubed. I want those extra parentheses there, otherwise it might look like it's x cubed, but it is not. It is g of x that is cubed. So looking at the numerator's limit, we can use the property where we separate the sum and do the limit of each term one at a time. The limit as x approaches 2 of 2f of x plus the limit as x approaches 2 of 1. Remember the limit of a constant times a function where we can pull out a constant multiple and multiply it to the limit. That is a strategy we're going to use here because we have a constant multiple. So instead of 2 being here, we can write it out here, and then we can do the limit as x approaches 2 of f of x. Using our graph of f of x, we're looking where x is 2, going up to the function and seeing that both sides are approaching the same value of 4. So that limit is 4. The next one is the limit of a constant. And remember, the limit of a constant is super easy because a constant function is only ever going to one place. So that limit is just 1. And then we put it all together for the numerator, and we've got 2 times 4 plus 1, which makes 9. Let's look at the limit of the denominator. Remember the property for powers, the limit of a power, where we can take the power of the limit. So going back to this one, we can rewrite that as the limit as x approaches 2 of g of x, and that limit we will cube. So let's go to the g function and see as x approaches 2 where the function is headed, and from either side, both sides approach the y value 2. So this is 2 cubed, or 8. Now, of course, we started by separating this quotient, numerator and denominator. Our numerator's limit is 9, our denominator's limit is 8. So our final answer, 9 over 8. The limit as x approaches 1 of f of x plus 3. Well, we do have a graph of g and we have a graph of f. We don't have a graph of f of x plus 3. This would be just f of x. But if we look at how x is approaching 1 and we think about direct substitution, well, 1 plus 3 is 4. So this is the same as saying the limit as x approaches 4 of f of x. Now we can use our graph of f of x, looking at where x is 4 and seeing that both sides do approach the same value and they approach the y value 3. 3 is our limit. The limit as x approaches 3 of f of g of x. This is a composition of functions. So remember that this will be equivalent to f of the limit as x approaches 3 of g of x, as long as f of x is continuous at the limit as x approaches 3 of g of x. Well, what does that look like? Let's start by finding the limit as x approaches 3 of g of x. We'll go to our graph of g, and we'll see where x is 3, and we go to the function looking from both sides. It looks like they approach the same value of 1. So that limit is 1. So now we ask ourselves, is the f of x graph continuous where x is 1? So let's go take a look at the graph of f, find 1 where x is 1, and we see there are no jumps or holes or breaks in the f of x graph at x equals 1. So f of x is continuous at x equals 1, and now we proceed by finding f of 1 because we found that limit to be 1, and it's f of that limit. F of 1 is the y value 5. Let's look at this other composition. The limit as x approaches -8 of f of g of x. Again, we can say that this is equivalent to f of the limit as x approaches -8 of g of x. But of course, we have to make sure that f of x is continuous at that limit. Well, going to the graph of g and finding the x value -8, we see that as going from one side to the other side and the other side, looking from each side, both sides approach the same y value of -1. So the limit as x approaches -8 of g of x equals -1. Now it doesn't matter, remember, it doesn't matter that there's a point down somewhere else. G of -8 has a different value than its limit, but that's not what a limit is. A limit is where the function is going. So now we have to ask ourselves, is f of x continuous at this limit? So we go to the graph of f, and we take a look for the x value -1, and we see that, in fact, there is a break in the function f where x equals -1. So f of x is not continuous at x equals -1. Therefore, this limit does not exist. D and E will be our answer. The limit as x approaches 2 from the right of the square root of 3x plus 1 divided by x plus 2. Now again, we have a quotient, so we want to do the limit of quotient property where we deal with the numerator and denominator limits separately. Now, it might throw us off that this time we're looking for the limit as x approaches 2 from a specific side. But remember, we always try substitution first. If it works, we are done, and we don't have to worry about looking for any other strategies. So let's go ahead and try that. For the numerator's limit, if I can plug 2 straight on in, and it works, looks like it can. 3 times 2 is 6, 6 plus 1 is 7, so that gives us square root of 7. For the denominator's limit, plugging 2 straight on in, 2 plus 2 is 4. No issues here. My denominator's limit is not 0, so now I can say that this limit if I put them back together, is the square root of 7 over 4, and I'm done. Remember that if direct substitution works, then the function is well behaved and it gets where it's going. So it doesn't matter if it's right side, left side, or both sides. If we can plug it in and it works, then we are done. Good job. Keep practicing.